Start with get up the whiteboard. So the two properties are the power property and the change of base property. Power property is the one we use a lot. It's extremely useful. It is, as far as I know, essentially what logarithms were invented to do, which is solve exponential equations for the exponent. Change of base property we'll talk about later. It's less useful. It lets you change bases of logs to other bases. And I am now realizing, looking at myself in the video, that my shirt is too much the same as the color of the blanket I've put on my chair. Anyway, we'll change shirts for the next video. Okay, so power property goes this way. So power property says that if I have log base b, and I'm specifying b here because it could be any base, like literally any. This works for all logs, including natural logs, common logs, which are log base 10, and any other legal log you want. So log base b of x to the p, so in other words, something to a power, is p times log base b of x. So in other words, if you have the logarithm of something that is raised to a power, you can factor the log out. It will, it just comes out. Now, this is derived from another property of logs that we're not going to talk about because that property goes with 3 other ones. And to really drive that home, you have to ask these weird questions that aren't useful. And I don't want to distract from the thrust of the class. So we're just going to stick to the power property. If you would like to see how this is derived, I'm happy to show you. It's actually relatively simple, and you can probably get it on the internet anywhere you want. Well, not anywhere. YouTube would probably be your best bet. Yeah, so for right now, just trust me. There's a couple things I do want to point out about this, which is everything inside the log has to be raised to the power in order to do this. So if I have, for example, let's say log base 2 of 5x to the third, I cannot factor that cube out because the third is not on the 5, it's only on the x. It has to be on absolutely everything. So this is not equal to 3 times log base 2 of 5x. That does not work. However, if I have this, actually, let me just to really drive the point home. Let's do the old red cross out. Don't do this. That. By the way, that is the super easy mistake to make, like incredibly easy mistake to make. On the other hand, let's say I have a natural log of 5x quantity cubed. I don't know why I changed log bases there. I'll go back to log base 2. It works with natural logs, of course. Oh, shoot. It takes my pencil away every time I try to erase. Log base 2, there, of that. So the whole thing is being raised to the third power. That is, in fact, 3 times log base 2 of 5x. You can totally do that because the whole thing is raised to the power. So you got to make sure that everything in the log is raised to the power before you do this. Otherwise, it breaks your problem. So how can we use this? How might we want to how might we want to go about utilizing this newfound ability to factor out exponents? Well, let me give you an example. So let's say I have a very simple question like 3 to the x equals 17. Now you might say to yourself, well, there's no x where 3 to that power equals 17, right? 3 to the second is 9, 3 to the third is 27. You jumped right over 17, and that's true. That means that there's no nice integer x for which this works, but there's a perfectly good decimal for which it works. So what I'm going to do is I'm going to, and this is going to be a recurring theme here, I'm going to take the log of both sides. Now, it does not matter what log base I use. Well, it kind of matters what log base I use because I'm going to need to put this into a calculator to find an actual number for it. Let me bring up the calculator that we've got here so I can point out a couple of features of it. Calculator, there it is. Calculator. All right. So when you're looking at the logs, there are 2 of them, just 2, and they are log and ln, right? So this is log base 10, and this is log base e, and that's all you got. So you want to use one of those because that's what you're going to put into your calculator. Now, you can use the change of base property to change logs, which we'll do a little bit later in this video. But it's an extra step. Why bother? You can use any log you want. Use a good one. I'm going to use natural log literally because it is one less letter to write, right? Instead of writing log, I get to write ln. Fantastic, one less letter. Okay, so here's what we're going to do. I'm going to go to somewhere, whiteboard, and I'm going to take the natural log of both sides of this. So ln of 3 to the x equals ln of 17. And then I'm going to use the power property to pull that x out. So x times ln of 3 equals ln of 17. That's an ugly 17, but it's a 17, believe me. And then I'm just going to divide both sides by ln of 3, which is a number, right? I know it's weird to divide by an ln, but remember that ln of 3 is just some number, right? So we're going to get x is ln of 17 over ln of 3, which I have no idea what that is. So I'm going to go put that into a calculator. And the calculator I'm going to choose obviously the one I have on the screen. So we're going to go ln of 17, close parentheses. Be careful about closing your parentheses, by the way. Some versions of the TI calculator will close them for you, but most will not. Divided by ln of 3, close parentheses. Oh, and if you don't close them, it assumes the dividing side is inside the log and everything, then your answer's all wrong. 2.5789. Let's say 2.58. So back to the whiteboard, about equal to 2.58. And lo and behold, if I go do 3 to the power of 2.58, I should get something right around 17. So I rounded up a little bit, so we're going to be slightly over 17, but not by much, right? It's just rounding here. So if I do like 3 to the power of my answer, 2.58, there you go, right? Slightly over 17, just like I said, because we rounded this up, so it's a little too high. Yeah, that's it. That's how you use the power property. We use it to solve exponential equations, such as this one. Now, you're not always going to get one as simple as this, right? And there's going to be a lot of word problems involved, which is really what exponential functions are for. There's a lot of real world things that are modeled by exponential equations, and so you really want to be able to solve them for the exponent, right? That's what it's for. That's why logs exist. So that's what we care about. So I've set up a problem on the next page here. Janet invests $1,200 at 4.7% per year. How long will it take her money to grow to $3,000? This is a totally valid question that you very much might want to actually know, right? And without logs, you actually can't solve this. Logs are how you get the exponent down, so you can actually work with it, basically. So let's do it. So I'm going to use the formula that we have that we found. I'm going to assume that we're doing this continuously, so I'm going to use this formula: A of t equals A0e to the RT. Now, you could certainly do it with the other one. Heck, maybe I'll do two. All right, I'll do continuously, and I'll do monthly as well. Why not? So if we've got A of t equals A0e to the RT, A0 is the starting amount, so $1,200. R is 4.7%, so 0.047. T is the thing we're looking for. E is E, and it's a constant. It's not a variable. And A of t is 3,000, right? That's the amount we want to end up with. So I'm going to have 3,000 equals 1,200 e to the 0.047 t. And then we're going to solve this. Now, a thing I want to point out here. So my first step before I do anything else, so my first step is to recognize what kind of problem I've got here. But then my first step in actually solving the problem is to divide the 1,200 over. So the first thing I'm going to do is this. So divide 1,200, and I want to show you why this is so important. So we do that, and 3,000 over 1,200 is like 30 over 12. So if I divide both of those by 3 or by 6, I end up with 5 over 2. Sure. So I end up with 5 over 2 equals e to the 0.047 t. Now, I made a big deal about why this is interesting. So here's why this is interesting. This 5 over 2 came from the 3,000 and the 1,200, but could be any set of values that have that ratio, right? If I had said Janet invests $2 million at 4.7%, how long will it take her money to grow to $5 million? It would be exactly the same amount of time, because when I do 5 million over 2 million, I get 5 halves. Right? I could have said Janet invests 2 cents at 4.7% per year. How long will it take her money to grow to 5 cents? It would be exactly the same amount of time. So you actually don't care at all about this or this, but only about this, only about the fraction of growth that you're going to experience. That's the only thing that matters. The actual values are irrelevant. I always found that kind of interesting. So I don't know if you find that interesting too, but yeah, it's just how much your money gets multiplied by is the only thing that you're really looking for here. So anyway, we're going to solve this equation largely the same way we did the last one. It's actually going to be even easier. We're going to use natural log again, of course. So I'm going to do ln of 5 over 2, or 2.5 if you like, equals ln of e to the 0.047t. And then I'm going to go over to the next page and rewrite that. So we have ln of 5 halves equals ln of e to the 0.047t. Now, I want to make a point here, and that is that this is a logarithm whose base is the same as the base of the exponential you're looking at. So I can use this property that if I have like log base b of b to the, let's say k, that's just k. Because remember what a log is, right? The log isn't saying what power do I have to raise the thing, what power do I have to raise my base to get the thing that's inside? Well, I have to raise b to the k to get b to the k, obviously, right? That's not some sort of trick. That really is the reason there. You can also think of a log with the same base as the exponential you're working with as sort of canceling it out, right? They're inverse functions of each other. So this is really f inverse of f of x, or it's actually f inverse of f of k, I should say, since I'm not actually using x's here. Hello, pencil, okay, right? And so just what we know about inverse functions is that f and f inverse cancel each other out, and you just get left with what you started with. This is k, right? This is what logs are supposed to do. They are supposed to cancel out exponentials. And natural log specifically cancels out e to the x. Just like log base 10 cancels out 10 to the x. Log base 2 cancels out 2 to the x, right? So this really says that the natural log of 5 halves equals cancel 0.047t. Divide by 0.047 and we're done. So t is approximately equal to something that I have no idea about. So I'm going to go to a calculator, right? So log of 5 halves over 0.047 is what I want to do. New share, please. So we're going to do natural log of 5 over 2 divided by 0.047. 19.49 years. So let's say 19.5 years. That's probably too long. Jenna will probably have to save some more money, but about equal to 19.5 years. So this is what logs are for. This is why this is why they were invented. This is what they do. There you go. This is, in my opinion, the best practical use of logs. They actually have a bunch of interesting uses in math, in higher math, but we're not doing that. I just want a nice introduction to these, and this is in a practical sense what they're really for. Yeah, let's let me do a different question. I'm gonna start a new board here. Actually, let me go ahead and pause so you don't have to just watch me write the question, which will be really boring. So I'm gonna pause. All right, I've got the problem written up and a shirt with a little more contrast with my blanket. Let's see what the problem looks like. All right, so I tried to do a decrease problem this time. So this is half-life problem. Carbon-14 has a half-life of 5,760 years. How long will it take a 10-gram sample to decay to 8 grams? So if you remember, half-life formula goes like this. It says amount at time t is equal to the amount at time 0 times 1/2 to the t over half-life. And we'll call it HL. Which in this case, so again, I know what I want it to end up at. It ends up at 8, starts at 10. So I'm going to have 8 equals 10 times 1/2 to some power. So t is the thing I'm looking for, divided by half-life, which is 5,760 years. So this is likely to take a while. All right, so the first thing I'm going to do, again, is the same thing as I did in the other example, where I'm just going to divide by 10, right? So I have to get it down to just the exponent, just the exponential function first before I can take the log of both sides. Otherwise, things get messy. So I divide by 10, I get 0.8, right? 8 over 10 is 0.8. 0.8 equals 1/2 to, that's not the right parenthesis. 1/2 to some power, t over 5760. All right. And unsurprisingly, well, I've got a variable in the exponent that I'm solving for. I think I should use a logarithm in order to use the power property to get that variable down out where I can work with it. So I am going to use natural log. It's my favorite one. So we're going to take natural log of 0.8 equals, I'm just going to pull the exponent down right now, t over 5760 times natural log of half. And you'll be unsurprised to find that I'm just going to solve for t. I'm going to divide by natural log of half and then multiply by 5,760. 5730? I think it's 5760. I don't remember. So I'll divide by log of a half. So we're going to have, I'm going to get a new screen here. We got ln 0.8 equals t over 5760 ln of a half. I don't know why I'm mixing fractions and decimals here, but it makes no difference. Divide by log of a half, ln of 0.8 over ln of a half equals t over 5760. And I'm going to multiply both sides by 5,760 to get t alone. So we're going to get 5,760 times ln of 0.8 or ln of 1/2 equals t. And so I'm going to go jam that in my calculator and see what I get. So we're going to go to calculator. So I have 5,760 times ln, where's the button for that? Do we have it? Is it S? Yes, ln of 0.8 divided by ln of a half. Bam. 1,854 years. About what we'd expect. Let's go back and write that down. So I'm going to ignore the decimal here and just say this is about 1854. Since this whole thing is an estimate anyway. Yeah, half-lives aren't that precise. So t is about equal to 1854 years. I was about to make a significant point that I wanted to make, and I forgot what it was. Oh, right. So when I get a number like this, what I really like to do is what I think of as a duh check, right? I check to make sure that my answer makes plausible sense. So here's my check in this case. So the half-life is 5,760 years. So I am expecting that after 5,760 years, this 10-gram sample would be 5 grams, right? So that's too long, right? Because I only wanted to get down to 8, not all the way down to 5. That's so I, instead of going 5 grams, it's only going 2 grams, which is like 40% of which is exactly 40% of 5. But I would expect something in the general vicinity of like slightly less than half of this, right? I'm thinking it'll take slightly less than half this time because this is like slightly less than half the decay I'm looking for. And that would be like, something less than 2,800 and we get 1,800, right? So obviously that's not a like accurate estimate of any kind, but this is totally in the range I would expect, right? This is absolutely in the general vicinity of the number I would expect. And so I use that to make sure I haven't made any like huge errors somewhere, right? So this seems like a totally plausible answer to me. You could also go ahead and take this and stick it back into the original equation, right? Take this and put it back in here, do 1/2 to the power of 1854 over 57/16. See what you get. Let's do that. So if I go 0.5 to the power of 1854 over 57/60, I should get something in the general vicinity of 0.8. That's very, very in the general vicinity of 0.8. I'm feeling pretty good about this answer. All right, great. So that's how you could do a decay problem. Now, one thing I do want to point out is decay problems can also be phrased as a negative rate of interest or growth. So let me pause the video again here. I'm going to write down another problem, and we'll do that one. All right, I've got the problem written down. So here we go. So we got trout in a large lake. There are 100,000 trout. I have no idea if that's a realistic population of trout, but let's just say that's how many there are. And it is declining at a devastating 18% per year. So we want to know how long until there are less than, or fewer than I should say, 50,000 trout in the lake. So what I've got here is a negative growth rate, right? The population is declining. So again, I'm going to use A of t equals A0 e to the RT. But this time, R is going to be negative 18%. So, oh, and I wanted to point out, I have sneakily turned this into a half-life problem, right? So there's, I want to know 50,000 is my goal number. Well, it's the number I'm going to end up at in this problem. And we're starting with 100,000. We've got e to the minus 0.18 times t. Okay, so note that I have sneakily disguised this as a half-life problem. My first step is the same. I'm going to divide by 100,000, and when I do, 50,000 over 100,000, 50 over 100, is a half, right? So a half equals e to the negative 0.18 t. So what I'm actually asking for here is, what's the half-life of this fish population, right? Half-life is not just for nuclear decay, or radioactive decay, I should say, although that's the context that you most often see it in math classes. Half-life is for anything that decays exponentially. There's actually a lot of things that decay exponentially, believe it or not. So for instance, the number of people using an old software, or an old version of software. So for instance, like there are still people out there who use Windows XP, which was like a thing when I was in college 20 something years ago, right? And some people, there are still people who use that, but it decays exponentially, which means that when the new version comes out, a lot of people adopt it really quickly, right? So it drops really fast, and then it levels off. But there's still people out there who use it, right? So then you lose a little percentage every year, but it never quite gets to zero. Now, in the real world, of course, eventually the last person will stop using Windows XP or whatever. But like in a pure mathematical sense, you never quite get to zero with exponential decay. So anyway, so the question here is, what's the half-life of this trout population, given that it's decaying at 18% per year? We phrase that as how long before the trout population is under 50,000, but it's the same question. Okay, so you're not going to be surprised at all about how I solve this. I'm going to take log of both sides. Yeah, let's do that. So ln of a half equals ln of e to the negative 0.18 t. Of course, I need a new board now. So we got ln of a half equals ln of e to the negative 0.18 t. And again, I'm taking the natural log of an exponential with a base of e. So the natural log and the e cancel each other out effectively. And so I get negative 0.18 t equals natural log of a half. And you might say to yourself, well, wait a minute, I can see what's coming next. You're going to divide by negative 0.18, and then the number you get is going to be negative. How does that make any sense? Aha, that's not actually what, so I am going to take that step, but natural log of a half divided by negative 0.18 is not negative. So let me show you why. So negative 0.18, negative 0.18. So that is in fact exactly what I'm doing. So I'm going to get t is approximately equal to, and of course we'll go to the calculator. So calculator says that natural log of a half divided by negative 0.18. So is that the negative? Yeah, 0.18 is 3.85. Why would that be positive? Right? I got natural log of a half, and I'm dividing it by a negative number. Why is it positive? The answer is natural log of a half is negative. Right? You have to raise e to a negative power to get something smaller than 1. So when you take the natural log, or any log, of a number that's smaller than 1, you always get a negative. So this ends up working out just like we'd want it to. So about 3.85 years. I might as well do this while I'm here. Natural log of a half is, by the way, about 0.67. Is that what it is? 0.69, something like that? 0.69, so about negative 0.7. Which I'm not going to go into right now, but turns out to have a lot of interesting consequences in the financial industry. They use 0.72 as an approximation for this, even though it's about 0.69, which is a little weird. Yeah, ask me about that in office hours sometime. I'll tell you about the rule of 72 and why it exists and what it is. Anyway, so natural log of a half is about negative 0.7. Okay, so let's go back and make 3.85 years. It's about right. So about equal to 3.85 years. So that's how long it takes half the fish population to die off. So almost 4 years. Not great. 18% decline is bad. You'll run out of fish pretty quick. Okay. That's all I really want to say about the power property. Notice that I'm using the power property each time to get the exponent out. I was not using it explicitly, right? Like the power property actually says you can pull the exponent out and use it as a factor, right? It says basically if what's inside the parentheses is raised to a power, then you can pull the power out, right? And we did that here, and we did that here probably. Or no, here's where I canceled for the first time using this this idea. Here we pulled it out again. Whether you pull out the exponent or use the exponent to cancel the base doesn't really make any difference. As you can see, like it didn't really change what I was doing in any of these problems. So whichever one you prefer, go right ahead. I like to think of, by the way, I like to think of taking the log rather than rewriting the log in exponential or the exponential in log form. But if you like to think of it as rewriting the exponential in log form, that actually works totally fine. I just find it weird. I prefer to like do something to both sides of an equation. That just feels more natural to me. Okay, so the other thing that I want to show you is the change of base property. So change of base property says this, that log base b of x is log base c of x or log base c of b. And you might say to yourself, all right, how is this helpful? The reason this is helpful is that you get to choose c. This works no matter what c is, as long as it's a legal log base, so no zeros or ones or negative things. So as long as this is a legal log base, this works fine. So for instance, you can choose it to be e or 10 and use your calculator, right? That's really what we're going to use this for. I don't want to go into too much detail on this. This is less useful than it used to be because you can actually calculate a variety of log bases on most computing devices. If you have a TI Inspire or one of the more advanced ones, like what are the numbers now, 89 or 91, I think, they'll just do different log bases. The more advanced HP calculators will do different log bases. I think Casio probably do too. Desmos will do different log bases. So if you're just looking to calculate a number, this is not that big a deal. Like this is not really that necessary anymore. If you're looking, there are some fancy math problems that you can do where this is super necessary. But for just calculating numbers, this is not as useful as it used to be. So we're not going to hit this too hard. I do want to show it to you. It is a thing that could come up in the future for you. So it's a quickie anyway. So let's do this. So here's my example. Let's say I want to calculate log base 2 of 3. Right? I want to know what that number is. Now, I don't know what that number is, right? So I'm going to say this is equal to x, for instance. Now, we could write this. I'm saying this is equal to x so that I can do this. This is to say that 2 to the x equals 3. That is a horrendous x. And so you can see there isn't a nice number that will work here. But if we could just solve this equation, right, in the way that we learned how to do just a few minutes ago. Or we can change bases. So let me show you how to change bases. So here's the way I remember this. I'm going to get rid of this stuff. So I want to change this base to something that I can put directly into my calculator, which is to say log base 10 or natural log base e. Now I've been using natural log the whole time. I'll go ahead and use log base 10 this time. Why not? It makes literally no difference. Let's pencil, please. So, computer, pencil, please. There we go. So what I'm going to do is I'm going to choose C to be 10. And the rest is just filling stuff in. So log base 10 is just log, right? So we're going to have log of the stuff on the inside, 3, over log of the base, which is 2. That's it. That's how you do it. Let's go find out what that number is. Log of 3 over log of 2. Apparently, it's about 1.585. There you go. And by the way, just to show you that you could have done it with natural log just as easily, natural log of 3 over natural log of 2. That says 22. Computer, I did not ask you to hit that. Delete. All right. Hey, it's exactly the same. What a surprise. So you can use whatever log base you want. It makes literally no difference. That works for all of them. Yeah, and this is how you can change bases of logs. If that ever becomes necessary for you, this is how you do it. I don't want to say too much more on that. So let's go back here, 1.585. What is it? About equal to 1.585. Now, let me make a point to you about where this comes from. This basically comes from doing the thing that I started with. So if I have log base 2 of 3, and I want to know what that number is, well, let's call that number x since I don't know what it is. Turn this into exponential form that says 2 to the x equals 3. My x's. It's an x. 2 to the x equals 3. I'm going to take natural log of both sides, or let's just take log base 10 of both sides. All right, so I take log base 10 of 2 to the x equals log base 10, 3. Use power property to factor the x out. X times log base 2, or base 10 of 2 equals log base 10 of 3. Divide both sides by log base 10 of 2. I end up with this. X equals log of 3 over log of 2. Lo and behold, that's exactly what it was, right? So the change of base formula is basically just shortcutting to the answer of changing this into this form and solving, right? So it's kind of just like like I said, just a shortcut to the answer when you're trying to solve something like this. So there you go. That's change base property. You choose whatever base you want because all log bases have this factor out, have the power property, and this is really just the power property. Again, it's just you're skipping all the work in the middle. So there you go. That's all I wanted to say about power property and the change base property. So I will see you guys in the next video.